that one. So, okay, let me start. So, stability and robustness analysis of control systems is a very important problem for control theorists. Therefore, it's a natural desire to obtain and to develop a toolbox that will help us to analyze these properties for as large class of control systems as possible. Therefore, one of the good candidates to analyze this in a large generality is the following class of control systems. So we will take the triple sigma consisting of three elements: the state space X, which is usually a Banach space, the space of inputs U, which is a Banach space as well, or at least non-linear space, and the flow map phi. And we call this triple a control system if it satisfies the following properties. If it has some local existence, so let's say for each initial condition X, for any input U, there is some time Tm such that the corresponding solution, well, so let's say this map phi of xu, it is defined on this interval from 0 to Tm. We also assume that this solution is a continuous map and that it satisfies a co-cycle property. So we need also some more axioms, but I don't want to put all these formalisms here, so the other ones are usually satisfied. I just say that this definition covers the ordinary differential equations, evolution PDEs with Lipschitz nonlinearities, broad classes of boundary control systems, time delay systems, and many systems of heterogeneous type, let's say the networks whose components may be ODEs, PDEs, etc. So, having the definition of a control system, we can define the stability property for these systems. We call the control system input to state stable, or shortly ISS, if the norm of the trajectory can be upper bounded as a sum of two functions. A function beta describing the transient behavior, it depends on the norm of the initial state and on the time. And also we add to that this function gamma of the norm of the input. And this function describes the asymptotic deviation of the system from the origin. So here beta decays to 0 when time goes to infinity. So this means that if time goes to infinity, this guy vanishes and the trajectory is upper bounded by this term. So you can see it here, right? So if we start somewhere here, this is my upper bound, it decays to this ball of the radius gamma of norm of u, and so our trajectory eventually approaches this ball. It turns out that this property is very important for nonlinear control of ODE systems, time delay systems, and more general infinite dimensional systems. And therefore, it is desirable to obtain a set of tools how we can analyze this property. And within the last several years, this set of tools was developed. In particular, we have direct and converse coercive Lyapunov theorems. We have so-called superposition theorems that characterize input-to-state stability in terms of the stability and attractivity properties. We have non-coercive Lyapunov formalism. We have integral characterizations of input-to-state stability, and for analysis of networks, we have powerful small-gain theorems. So that's actually amazing how much we can do on this very abstract and general level without assuming any structural properties from our control systems like linearity, monotonicity, or things like that, and also without assuming some particular type of dynamics, like time delay systems or only ODEs or only parabolic PDEs, so very general. But we have to pay for that. What do we pay? We pay actually that the question appears how we can apply this for particular models. And in fact, we need to do something. In order to apply all this machinery, first of all, we have to verify that our model is actually a control system. So we have to verify well-posedness of that system. We have to verify co-cycle property and other axioms of control systems. But that's not enough. I mean, it's only a starting point. Actually, we need more. We need also some properties of the flow map. For example, if we would like to apply any kind of Lyapunov arguments, then we need to have in advance that uniformly bounded trajectories are uniformly bounded solutions are global, so defined for all times. Otherwise, we cannot prolong the solutions defined on finite time intervals. For non-coercive Lyapunov methods, we need boundedness of reachability sets, so that this flow map phi maps bounded sets into bounded sets. For some other results, we need the regularity of the flow map. So, to take it short, if we want to use all this machinery to study stability and robustness, then we need to have in advance a whole bunch of properties of our flow map and of our control system. And I mean, for any particular class, we need to verify them. There are some partial special cases where we know all this. For example, we know this for ODEs, or for time delay systems, it is also well developed, this theory. But for example, for PDEs with boundary controls, which are for nonlinear PDEs, we do not have such a general theory. And what we would like to do today, we want to develop conditions which guarantee these properties for quite a general class of semilinear infinite-dimensional systems. Namely, what we are going to consider is such a class of abstract control systems. Here, A generates a strongly continuous semigroup T of T on a Banach space X, which is our state space. U, which is a space of input values for us, is also a Banach space. The inputs we assume to be from some class LQ. For most part of the talk, we will have L infinity inputs, though. F is some nonlinear map which is defined on the whole X times U. Okay? And B, so this guy, is an unbounded operator mapping U to X. But since it is an unbounded operator, it may not be defined on the whole U. But we assume that it belongs to the class L from, it is a bounded operator from U to X minus 1, where X minus 1 is extrapolation space. So basically we take the closure of X with respect to this norm. Okay? So that's an idea. So basically B is a bad operator from U to X, but if we make our X large, if we extend it, it becomes a good operator. So that's the logic. This class of systems, well, I have learned it from this paper by Felix Schwenninger, where he has introduced it and studied for parabolic boundary, parabolic systems. Okay, and well, there were some also more general results. Basically, he was interested in global stability analysis and ISS in this paper. So here we shift basically, and we would like to have some more to know more about the properties of the flow map. So, okay, why I find this class of systems interesting? Well, first of all, it is general enough. So it still covers quite big classes of control systems, like linear boundary control systems, PDEs with distributed inputs, ODEs, switch systems, etc. And on the other hand, it still has quite a nice structure so that it is tractable. So we can really study and obtain powerful well-posedness results for that. Another reason why do I like this class of systems is why in the last years, the general ISS theory for infinite dimensional systems has, let's say, divided into several subfields. Because basically there are several classes of systems which are studied by separate methods, and well, they developing like on theories on their own. For example, a great deal of research was devoted to linear systems with unbounded operators B. This is a model for, let's say, PDEs with boundary inputs, for linear PDEs with boundary inputs. And the input space is usually some space LQ. In many papers, L2, so some integrable inputs. At the same time, if we deal with non-linear infinite dimensional systems, then many papers are devoted to this type of systems. So we have here F, but F is usually Lipschitz continuum, so quite nice. And this continues with respect to U. So here we do not have boundary inputs. Let's say we have distributed inputs. And they are usually assumed to be continuous or piecewise continuous. So you see, so these are really quite different types of systems. And if we go to the classical theory of ODE systems, then it deals with non-linear systems, but L-infinity inputs. So, I mean, just formally, this class of systems is actually also not a special type of this one, because here we have continuous or piecewise continuous inputs, and here L-infinity inputs. So, actually, I don't like this situation because it seems to me quite artificial, and I find it would be really nice to have a unified well-posedness theory, which would cover all these three cases. And this is what we are gonna to deal today. So our aim is to derive sufficient conditions for local existence and uniqueness for these semilinear evolution equations. We would like to develop conditions for well-posedness of these equations as control systems and to study properties of the flow maps. Also, we would like to see how that class relates to boundary control systems, and finally, how this helps for stability analysis, which was our motivation. Okay. Well, first of all, we need to define the concept of solution for that class of systems. And before we do that, let us look how this works for linear systems. Let us forget about the nonlinearity F. So now we have this class of systems, and A, as before, generates a C0 semigroup on the Banach space X, and B is unbounded operator from U to X, but it is bounded from U to X minus 1. How do we proceed? How we define solutions? Well, a nice thing is that we can extrapolate also our semigroup T from X to this larger space X minus 1. And this will be our semigroup T minus 1, and this extension is unique. And what is now fine? Now, on this space X minus 1, this system is well-posed because operator B is a bounded operator. And we can just write down the formula for mild solutions of this system. And here is that. Okay? So this for all initial condition x0 for any u from L1 lock, we can define mild solution. Furthermore, one can verify actually it satisfies co-cycle property and all other properties we need. So basically this is a control system on x minus 1. Well, but it's not quite what we wanted, because now the trajectories are in x minus 1 in this larger space, and we want trajectories in x, in our original space. Well, but this is not what we get for free. And we need to assume more. We need to make further restrictions on our operator B. And here comes an important definition. So the operator B is called Q-admissible for our semigroup if such a property holds. Basically, it means that for all u from the space LQ, our trajectory is well defined. Well, this is how the people from functional analysis call this property. In terms of the systems theory, what is written here is forward completeness for inputs from LQ space. Okay? Well, in fact, from this forward completeness, we can get even a better property. One can show that for each time t, we can bound this term u, well, this term, which describes the influence of an input. We can bound it by some constant h, depending on t, times the norm of the input. Okay? So why it is very nice? Because it gives us boundedness of reachability sets. This means that our mild solution that we have defined for linear systems stays bounded if we start from bounded ball and apply uniformly bounded inputs. It's important. Okay, so that was our motivation, the analysis of linear systems. Now let's go back to our class of semi-linear systems. Now we have this nonlinearity, and now we already know that to have some nice theory, we need to assume some good properties from B. And we assume that it is infinite admissible. So this means that this map is well defined and it maps to X for inputs from the class L infinity. Okay, so it should be here L infinity. We also assume that this map is continuous. There are some nice sufficient conditions for that. I don't go into details. So this is what we need to assume from B. But we need to assume something from F. Well, at the very least, since we would like to integrate these terms, we need to assume that for all L infinity inputs and continuance X, this map is integrable. Okay. Now we can define finally the concept of mild solution. A continuance function will be called a mild solution of this system if X solves such an integral equation. Well, okay, solution subject to given initial condition and given input. So the continuance solution of this integral equation we call mild solutions of this system. Let us look one more time. So what do we have here? So this is influence of initial condition. Since T is strongly continuous, then this guy is a continuance map. This is continuance because we have assumed that. And finally, this guy is integrable. And because this is integrable for our fixed X and U, then this whole guy is a continuous function of time, which is a standard result. So all this right-hand side is actually a continuous function if X is continuous and U. So this shows that actually this concept of solution is meaningful. Well, clearly the integrals we understand in the sense of Bochner. Well, okay. Now to have existence uniqueness, we need some further conditions in F. And it is natural that we need some kind of Lipschitz continuity. We will assume that F is Lipschitz continuous in the following sense. For any C and any xy from the bounded ball of radius C, for any inputs of magnitudes bounded by C, we have this property. So also we assume that this function F is continuous with respect to the second argument. Finally, we would like to have such a bound for F. So basically it tells that F of 0 and point, it maps bounded balls into bounded balls. This is the meaning of this estimate. So we define ball of radius R around Z by this formula, well, as usual, and this we will use for the set of inputs with essential image in the set S. And now we proceed to our first result. So pick, well, since T is C0 semigroup, it can be upper bounded in this way for some M and lambda. And also we know that because of infinite admissibility of B, we have such a nice inequality. And since this H is increasing in time, well, we can always assume that we can compute such a limit, H0, right? So what is the meaning of this parameter H0? Okay, this guy, it describes the deviation of the trajectory due to this control operator B. Okay. Clearly, we have assumed that for each given U, this map is continuous in time. Well, it is 0 at 0, clearly, and continuous. So each particular U cannot drive us very far away in infinitely smaller time. But if we take nu and uu, they can drive us from, let's say, undisturbed case faster and faster. And this H0, it describes basically the worst case scenario. How far away we can drive our trajectory from the undisturbed trajectory if by applying input u of this magnitude. Okay. And now we have our local well-posedness theorem. Pick any bounded ball in the state space. Take any bounded set S and any delta. Now there is a time t1 which depends only on this data, such that if we start in each point of this ball, and if we apply any input whose essential image is in S, then we have a unique solution on 0t1, and we can even say where this solution lies, namely in ball with this radius. So actually, this is the main difference of this Picard-Lindelöf theorem in this my variation from the classical one. So usually, Picard-Lindelöf theorem states that if we start in some bounded ball, apply some bounded inputs, then we have uniform existence time. So here we can actually manage that we do not have only uniform existence time, but we also know where will our solution stay within this time. And it helps for further analysis, actually. But note that although we start in a ball of radius r around some point, then we will leave in the ball with a considerably larger radius, right? So here we multiply our original radius by m, also add this term and also this delta. And actually, it is not possible to improve this result. Because first of all, our semi-group can increase the magnitude of their state quite rapidly, let's say infinitely fast, because we do not have uniform continuity of the semi-group. And also our input operator can, within infinitely smaller time, drive us away from our initial point. So actually, it is not possible to improve this result. But okay, in some special case, we get a better result. So just in a straightforward way, if our operator is zero class admissible, so this H0 is 0, and well, there are pretty many such operators. It's not a very small class. For example, if our semi-group is analytic, then this is quite often the case. Okay, so if operator is zero class admissible, so it cannot drive us infinitely fast from our trajectory. And if in addition, our semi-group is quasi-contractive, so it satisfies such an estimate, with here coefficient m equal to 1, then for the same data as before, we can verify that there is some time t1 such that the solution lies in the ball of radius r plus delta. So basically we can, for any original ball, we can take a bit larger ball and we can find uniform time for existence. And at the same time, we stay in that delta ball. This is what we have. Okay, just note it is still important that we have a bounded ball here. If I will just write bounded set in the state space, the theorem will be wrong. And there are counterexamples for that. Well, and now we go to our first takeout message. Assume that we have our state space is a Banach space, U is a Banach space as well, and our input space is an infinity maps from R plus to U. We assume that this map is integrable, and we assume that B is infinite admissible and F is Lipschitz continuous. Then for any initial state and any input U, we have unique maximal solution, which we denote in this way. Furthermore, this triple is a well-defined control system. We have cocycle property, and furthermore, if it is defined on finite interval, so if the maximal existence time is finite, then the solution goes to infinity when t approaches this time. And furthermore, if f is at 0 is 0, then phi is continuous at the equilibrium. So this is, let's say, it gives us some basic set of tools or basic set of properties that we can exploit for stability analysis. We can do a bit more also. Well, we say that the system is forward complete if the trajectory is global for all initial condition and all inputs. And we say that the system has bounded reachability sets if the phi maps bounded sets of if the initial state is bounded, U is uniformly bounded, and T is on the bounded set, then the corresponding reachability set is bounded as well. Well, note that for linear systems, forward completeness implies this property, also in infinite dimensions, but it is not so for nonlinear systems, and there are counterexamples for that. Well, and here I just give a slightly restyled version of the theorem by Felix Schwenninger, which was published 2 years ago. So if we assume all what I assumed previously, but F is globally Lipschitz continuous, then we have actually forward complete control system satisfying boundedness of reachability sets property. Well, clearly, I mean, this is quite a rough sufficient condition. So it is not that we would like to have global Lipschitz continuity as our nonlinearity, but this is what we have right now, and actually it's a very complex problem to characterize this boundedness of reachability sets. For ODEs, it was shown in this paper by Andrii and Zonta, and it was shown that under some natural assumptions of nonlinearity, forward completeness is equivalent to boundedness of reachability sets. And one can give a characterization in terms of Lyapunov functions. And actually, for time delay systems, this property is very important. So this question whether forward completeness is equivalent to boundedness of reachability sets is essential in order to answer the question whether global asymptotic stability is equivalent to uniform global asymptotic stability. So let's say characterization of this property is really an important open problem. And this is just a sufficient condition for that. But if we have this property, if we have the boundedness of reachability sets, it helps us a lot. In particular, it helps to get some further properties of the flow map. We say that the flow of a control system is Lipschitz continuous in compact intervals if we have such a bound for all times on a finite interval and all x1, x2, which are from the bounded set. So, okay, let's say for any c and any time tau, we have L such that we have such a bound with a Lipschitz constant, which depends on the size of the initial states and the size of inputs and the maximal length of the interval. And this property is important, for example, for converse Lyapunov theorems. Therefore, we're interested in this property. So, and what we have, I mean, if all assumptions that we made for well-posedness, so infinite admissibility, local Lipschitz continuity of F, if we have all that, and if the system has boundedness of reachability sets property, then actually our system will have this Lipschitz continuity of the flow, which is good news for, as I have told, that analysis of Lyapunov analysis of such systems. Okay, so now we go to our takeout message 2. So how all this helps to stability analysis. Assume that we have these conditions which we used for local existence uniqueness. Under the same conditions, now existence of cursive ISS Lyapunov function implies ISS. Existence of a non-cursive together with boundedness of reachability sets implies ISS. We have such ISS superposition theorems and also some integral characterizations. Well, I know that I have not defined all these properties. It's just for those who are within this ISS framework. But the message is, if we have these structural conditions for the linear operator B and nonlinearity F, then we can apply all the machinery that has been developed through the last decade in the infinite dimensional ISS theory. So that's the main point of this slide. And this theorem follows from the main results here and the well-posedness assumptions, well, the well-posedness results presented before. Well, okay, fine. So what we have reached till now, we have obtained the well-posedness theory and also the stability ISS theory for that semilinear equations. But well, the typical PD control systems look very differently. I mean, they don't look like that we have one equation. We have equation and we have also boundary conditions. So, therefore, what we need to do next? We need somehow to transform these boundary conditions here to the equation. And we have to do it in a quite general way. Well, very nice that the theory of abstract boundary control systems give us a way how to do that. First, let us think about very classical setting of linear boundary control systems. So let XU be Banach spaces, we consider such a system. X dot equals this A hat X, and we have here this equation. This guy is called often formal system operator, and it is a linear operator first. And this is called boundary operator. It is linear and it is defined on a domain which is larger than domain of this guy. And we call this linear boundary control system if the operator A, which is basically the restriction of the formal system operator to this set, to the kernel of R. If this A generates a C0 semigroup. And also we assume that there is a bounded operator R, which is the right inverse of this boundary operator. Okay, so if this holds, then we have linear boundary control system. And now we can define also semilinear systems, which is what we wanted to. And well, this definition is actually by Felix from his paper. So we add now this nonlinearity. And if A, this formal system operator and boundary operator satisfy, well, form a linear boundary control system. And if we add this F, then we call this semilinear boundary control system. And now it turns out, assume that we have a classical solution of this system. So namely, we have some C1 map, which after substitution makes all these two relationships valid. Any classical solution can be represented for this boundary control system in a variety of ways. In particular, it can be represented in this form. for any C2 input U. Well, and when we look at this formula, then we see that this is something we are familiar with. Namely, this is precisely the formula for mild solutions of evolution equations, where the input operator is given by this guy. And nicely enough, in this representation, this operator is always a map from U to x minus 1. Well, a bounded operator. Very nice.
Andrii, can I ask a question here?
Yes.
Comparing the two red things, so you have phi of tx0u on the left.
Yes.
And then the red integral terms, and there in the second integral, we have f of x of r.
Okay.
What is x? Is x equal to phi then, or?
Yes, right. X is equal to phi, and also we have here now the input w. So I have just divided this boundary input and distributed input. Okay. So basically we have here combined input. So okay, so here could be u and w as well, and w also C2.
Right. I mean,
but yes, you're right.
Then that's not really, I mean, representation. That's an implicit formula for the solution, right?
Okay, because let's say each classical solution must satisfy this relationship.
Okay, thank you.
In this way, it must satisfy if f is continuous, the inputs, well, u and also this guy w are C2, and also we have some initial condition which satisfies this property. So under some conditions, reasonable conditions, the classical solution satisfies this equation always, this integral equation. And now we can just take this formula as a definition of a mild solution for this boundary control system. And we say, okay, that for all uw from L1 log, for all any initial condition from x, we will call a continuous function satisfying this integral equation a mild solution of our semilinear system. Okay, so here should be xs and w of s. Okay. Our linearity. And b here is precisely this operator, which is written here, which is defined by means of formal system operator and boundary operator. Well, and what is now good? This basically means that all semilinear boundary control systems can be written as semilinear evolution equations. And this means that all what we have defined previously works for semilinear boundary control systems. One more time. Mild solutions of this guy are mild solutions of this guy with W. And everything works for this class of systems. And now I come to conclusions. What we have considered is such a general class of semilinear evolution equations, where F is nonlinearity, but it is nice. It is Lipschitz continuance in first argument, continuance in the second one. And B is linear operator, but not that nice. So maps U only to x minus 1, and it is unbounded as an operator from U to x. But if we assume that B is infinite admissible and F is Lipschitz continuance, then we can show that this system is a well-defined, well-posed control system. We can verify the basic properties of the solution map that we need for stability analysis. Let's say for Lyapunov analysis, for ISS superposition theorems, and it allows to use all the machinery that was developed for abstract control systems for its ISS analysis to analysis of such systems. Well, the main references are basically this survey by me and Christoph, where it has summarized the state of the art for ISS theory, and this paper by Felix, where he has introduced this kind of boundary control systems. Also, well, for ISS characterizations that I have presented, they are based on these papers where the superposition theorems for ISS property were shown. The non-coercive Lyapunov theory for ISS was developed. And now let me go to some outlook. Well, let me tell, after all the things which were quite nice, let me tell one thing which is not that nice about that class of systems. Namely, we have assumed that F is defined on the whole X times U. Well, it seems like a rather natural condition, but in fact, it rules out many nonlinearities. If X, our state space, is L2, then just this square map is already not well defined, because it maps L2 to L1. And it is, I mean, it's, so we cannot, let's say, consider many nonlinear systems on L2 then straight away. Okay, if we assume that X is a space of continuance functions, then that will be well-defined map and we can do all our analysis. But for this quite classical choice, quite standard choice, our analysis just will not work. For example, we cannot analyze with this in this way the parabolic systems with polynomial nonlinearities. But what one could do, one could consider such a theory for analytic systems, where F does not have to be defined on the whole space X, but just on some space X alpha, where this guy is a fractional space, well, which is something in between the domain of A and the whole space X. And it is enough that F is defined just on this set to make a nice well-posedness theory. So, and clearly we would like then to provide a general toolbox for analytic systems. Well, then also what I have not presented here at all is about converse Lyapunov theorems. So what would be nice to have is converse Lyapunov theorems for this class of systems. What is another thing is that even for linear system, if we do not have F, then we do not have converse Lyapunov theorems in case if B is an unbounded operator. And I mean, it's quite disturbing because we don't know how to apply Lyapunov methods for analysis of boundary control systems in a systematic manner. So for some systems, it is okay, but for some systems, it just doesn't work okay. And we would like to know why. This is one of the research directions. Well, and finally, another thing what we would like to know is whether we can verify input to state stability of, let's say, systems with a stronger nonlinearities, like for the Viscous-Burgers equation with Dirichlet-Neumann boundary inputs. So Jun Zheng, who is also here in this virtual room, so he has actually studied this problem and he has obtained that one can get input to state stability if we have some bounds for the inputs. So he has done it using the technique of the Georgi iteration, but as long as I know, there is still no global result. So neither in positive way that the system would be ISS, nor in the negative way. And it would be really nice to have one, and we hope that with the Lyapunov technique we would be able to get that. But many problems have to be solved before that. Well, so this is basically the outline of what I would like to do next. And if you're interested, well, it would be great, nice to cooperate. And if you would also go in this direction. So thanks a lot for your attention, and I'm looking forward to your questions.